All right, so last week we talked about velocity kinematic and how we can use Jacobian to write our velocity kinematic expression, right? So the rate of change of the input will change our output with respect to our Jacobian matrix. So Jacobian is the mapping between the rate of change of the input to the rate of change of the output, all right? If you're reading your book, it says, I think the screw motion or something like that, which is omega and v, is the same thing. So it says v equal to j theta dot, which is your v is omega and v, which is the velocities. So we are saying the same thing. They're using a different notation. Now, we talked about the direct method and also how to drive Jacobian directly ourselves from a robot, right? There are two other methods that you can use. So today's class is basically just giving you more tools if you wanted to drive velocity kinematic, all right? So the definitions are already set up last week. These are just two new methods. One is, we call it explicit method, and the other one is the implicit method. So this is actually the implicit method. I don't know why I wrote explicit, because this is my old lecture. So in yours, it says implicit, right? Yeah. So implicit, explicit. Explicit means that it's very clear what you're doing. Implicit is just less clear vague. And the reason is that you will see that in the explicit method, we use the position and orientation of the end effector, which we will use for Jacobian. This one you use kind of like the last method, walk through all the joints. So we learned two methods last week. Where were they called? If you remember, direct method and then velocity propagation, right? So you said, what is the velocity at every joint? Then you find the velocity of the end effector. Let's find that relationship between them, which is the Jacobian. Now here we are going to walk through the joints, but this time we will drive those the elements of the matrices directly. One from the linear velocity, one from angular velocity. So in every robot that we deal with, in robot manipulator, the joints are either prismatic or revolute, right? So we're going to base it on that. We're going to develop a relationship for prismatic joint, develop a relationship for a revolute joint. Now, there could be linear velocity and angular velocity. Same things, right? We talked about this before. But we're going to see the distribution of each. And then we will put them all together, and then that becomes our implicit method from the Jacobian method. So if we have prismatic joints, our linear velocity would be v, right? Let's say v. I will call it j for the prismatic joint. If you have a prismatic joint, what is the contribution of prismatic joint in angular velocity? Right? There's nothing. Now, if you have a revolute joint, the contribution to linear velocity could be, if you remember from last time, omega I cross product of pi. P was the distance between our revolute joint to our previous joint that we were discussing, right? So we are using the same element that we already talked about, nothing new here. What is the contribution of revolute joint to our angular velocity? This omega I capital. Omega I capital had theta I and the axis, the direction, right? So this already is assuming the direction inside of it. Now, how do we use this to find the implicit method? We are going to introduce epsilon I as epsilon I is 1 if we have prismatic joint. Epsilon I is 0 if we have revolute. Now, what would be epsilon I naught? So naught 1 is 0, right? For prismatic joint would be 1 for revolute joint. So this implicit method is very good when you're writing the code, when you're programming, because all you need to ask is this a prismatic joint or not? Then you give it 1 or 0, and you can write everything. If it is 0, it will be multiplied by whatever is 0. There will be no contribution. If it was 1, there will be contribution. All right. So the whole idea is to develop our algorithm as we are introducing this method. Now, once we define epsilon I and epsilon I naught, the end effector, so this effector is end effector. Our end effector linear velocity will be the summation of epsilon I times vi. If epsilon I was prismatic, so it's 1, is the direct linear velocity, plus epsilon I naught, right? Omega I cross product of p, which is the distance. Epsilon I naught for prismatic is 0, for the revolute is 1. So for the revolute that there is a p defined, there's an offset that will have a value. If it's 0, then it will be 0. Then for the end effector angular velocity, we only have the revolute joint, right? So that's epsilon naught multiplied by all the omega i's. These two, we can even expand them more and factor out our q dot I out of it. So from here, if you have a linear velocity, you have again the value and the direction, right? The axis. Same for here, you had an axis and a q dot, so theta dot or d dot. If we use the generalized form, just say q dot the velocity. We take that out. All we have here is if this is prismatic or revolute, what's the axis? Plus the opposite if it's revolute or prismatic, axis cross product of the distance. And this is the summation multiplied by joint variables. Then omega will be also omega capital. So q dot I, which can come out, factor out epsilon naught I and zi, which is the directions. So all matters is that a revolute joint? Yes. Then we count it. If it's not, it will be plus 0 in there. Yes. Yes. So basically, you're again walking through how many joints I have. Is it revolute? Yes. So there is angular velocity. It's not revolute plus 0. So you're still counting it, but giving it 0. So it's more generalized. You can, because some of you asked, I think it was Chintian, you asked that, no, maybe someone else, I don't remember, maybe you see one, that do we use this for a general configuration of a robot or for this exact robot? All right. Now that you know this, for your next assignment, you can write for a general robot. Because this is where you're introducing the configuration, the CIs, right? So as we go forward, your programming assignment will be more, not complicated, like more generalized. So we are starting from very specific examples to go up. At the end of this, you should be comfortable getting a model and just analyze it. Doesn't matter what it looks like. All right. So we're going toward that. Now, this is your implicit method because you're saying that I don't know what every joints are. I'm going to write a relationship, and for those that doesn't match, I'm going to put 0. If there's a value, I'm going to put the value. So you have no idea what the robot looks like. Then for Jacobian, or for your V and omega of your end effector, which you could say it's the generalized screw motion, you will have J of V and J of omega, which is the linear portion of Jacobian and angular portion of the Jacobian times your Q dot I. I goes to N, number of the joints. Q dot is your velocity. And so you have one side velocity, Jacobian times the input velocities. So you've seen this before. We derived this differently before in 2 different ways. This is a third method. So this is still the implicit form. This is basically expanding what you just saw And you see that that will be the linear portion of this is the angular portion of your Jacobian. Now, you could think of this is your explicit form. This should tell, does that say in your lectures explicit? Okay, so I added that. So now what is explicit? So what we said that Jacobian is the velocity of the end effector, right? So what if we have the transformation matrix of the end effector? Exactly know the position and orientation. Jacobian was the rate of the change, right? If we get the rate of the change of the matrix, then we have Jacobian. This is very, very clear. We're talking about end effector, velocity of end effector. Let's just find the rate right here. So, this case, you have to have the configuration of your end effector. So, I will show you an example that will give you the configuration. We will also on Wednesday we will start learning about pH method, which basically is finding the configuration of end effector. So if you have used pH method, if you don't know what it is yet, some of you know, best way to find Jacobian is to use this method. If you have POE, use any of those three methods we talked about. Right? So this says that Jacobian for the linear is to find the position of your end effector and then find the rate or differentiate with respect to all the variables. If you want to which is all the angles. Then for the last three, for the angular, just put the angular velocity direction, which we have done before, right? Because they are the revolute joints are the only one that contribute into the angular velocity anyway. Now, sometimes you will see in literature that we will find our basic Jacobian in frame 0, base frame. If you're following your book, it says base Jacobian. It just means in respect to a fixed frame. So we have just done that. So for you all, you know about Jacobian in frame 0 or in the base frame. You will see sometimes that they put that what frame they are finding that in, so that will go outside and top. The different notation. Oh, it means that this Jacobian is the basic Jacobian calculus in the base frame. Because if you remember, we could find Jacobian in other frames. You actually don't have to do it. You find this one and then use the rotation matrix to find out like the velocity from a specific frame. And we talked about why it's that important, right? All right. So this is an example. You're given a certain, so for a given, for a certain RPR manipulator, how many joints? 3. What are the joints? Revolute, prismatic revolute. Now, this can have different configuration, right? They're kind of different robots could happen here. But we have the following transformation matrices. We have the T of 0 to 1, 0 to 3, and 0 to end effector. All right? So end effector is the further. So we have these three transformations. So meaning that which one of them is the end effector in base frame? This one, 0 to E, right? From this, we have the position of the end effector, right? The last column, the first three, and we have the rotation matrix for that as well. So since we have this information, we can use the explicit method to find the Jacobian. So they want to drive the basic Jacobian relating joint velocity to end effector linear angular velocity frame to 0. The basic Jacobian, once we have it, we just say omega and v and omega equals j times theta, right? Now, we know the best way is to use explicit method. Going back to explicit method, what did he say? What do we have to do? This is the part that math becomes really important. You have to find a way to marry math and fun. Huh? Yes. Otherwise, why would I keep this? Yes, it's fine. Okay. You saw, okay, I don't know how you like take on live, but when I did this same programming assignment you did, when I see the robot is moving, I was ecstatic. I was super happy. I could go from something on the paper and I could give it life. And it can move, you know, and I could analyze. For me, that was fun. If this doesn't bring you fun, we are 7 more weeks of data. So maybe we can find fun somehow. So robotic is all about math, but we have like a level of math. So I try to keep it simple. I try to open like the simplest way that I could teach this, I'm teaching it. If you sit in other robotic courses, this can be a lot more complicated. If any of you have experience with robotics, you see that the math is a lot more complicated. But you bring it down to differential equation and one at a time, with respect to one variable at a time. I'm not even asking chain or anything. All right. So give some love. So partial of x of p, the position of end effector with respect to qy, the first joint. So you look for the first variable and get the partial with respect to that, and then you move on. Right? So how many items you have in the position? Let me correct that. So you have differential p. That's not just one row, right? How many rows is that? 3. X, Y, Z, right? And then you have different joints. Q1, theta 1, theta 2, theta 3. So I'll have to find what represent X position. Let's get the differentiation with respect to all the variables that we have as joints. And then move on. That's what we're going to do for the example that we just saw. All right, I'm going to make this a little bit bigger so you can see how these look like. Maybe find the fun in there. So C1, as usual, is cosine of theta 1. S1 is sine of theta 1, and so on. Now, from T01 is the transformation of first joint, right, with respect to base spread. Can you tell me the axis of rotation? Like, what is your axis of rotation? What's your Z? What's the one that you, which axis your joint is rotating about? Not. You've seen them before. There's nothing. So when we talk about rotation, what do we look at? Top 9, right? Does this look like something you've seen before? Yes, rotation about Z, right? Ah, that's what I was gonna do there. So this is your Z1 seen in frame 0 because we are just talking about basic Jacobian, everything from frame 0. Then for this one, this is our rotation, right? So this one is the Z3 in frame 0, right? And then for this one, that's the Z of end effector. And we have the position of end effector. This is your PX, or P position of the end effector. I'm going to say PE. PE is PE X position, PE Y position, PE Z position. Okay. Since this is PRP, I'm going to say my view, it could be, well, I'm looking at the numbers, theta 1. Then I have D2. So I'm going to say the second one is D2 and theta 3. Could you use theta 2? But if they named this theta 2, then that would have been the prismatic, but they call it B2, so I'm gonna just use B2. So I identified my variable, my joint variables. I identified the position of my end effector. I found the axis of rotation. And then I also know this one is ZE as seen in frame 0. So I have all of this information. I'm going to use the explicit method because like I have the information. So I need to find JV, J omega. I'm going to write it as brackets so you know this is the matrix. So if you think about it, I'm going to divide it in 2 parts because I have revolute and prismatic. Sorry, I have linear velocity and angular velocity. Now, let's start with the easy one. Which one is the easier one? Is it the angular part of this matrix or the linear part of it? Angular? It is, because all we need to know is the direction of the axes, right? We have 3 joints, we need 3 directions. What is the direction of joint 1? Z01, right? So I'm gonna write Z01, but you know that we have 001. So we already have that information. Z1 as seen in frame 0, in base frame, because this is our base Jacobian. What is the axis of rotation for your second joint? 0. Why? It's a prismatic joint. All right. Easy. That's why it's the easy part. Because you just need to look at the robot. What is the third axis of rotation from the base frame? Z3, as seen in frame 0. We also have that information. So the easy one is usually is because you either can look at them, you have their information readily available to you. So we took care of half of this. Now the other half, we have the information, we have to do a little bit of math now. So the first one is partial differential of PE, position of end effector with respect to what? Theta 1, your first variable, PE with respect to D2, your second variable, PE with respect to your third one, theta 3. These joint variable came from us looking at those matrices, and from the problem is RPR, so it must be 3 joints. You just need what they call. Now the rest is math. With the partial differential with respect to those joint variables. Now, if you are not able to get to this, doesn't matter how good you are in math, you can't do it. So if you're using math as a tool to give us a solution, but it doesn't do this for us. Now I want to volunteer to do this math for us. I mean, I've done it. So let's write the second part. Yes, it's already done. So let's write this one, right? So I'm going to write J omega down here and bring the information from what I have, 001, 000, cosine 1, cosine 3, sine 1, cosine 3, negative sine 3. Now for JV, which is the top part, this is JV part, this is J omega part. We have partial of x position L1 cosine 1 plus L2 cosine 1 cosine 3 minus sine 1b 2. This with respect to theta 1, then partial of y position D2 this time, that was our second one, then negative L2 S3, which is sine of 3 with respect to theta 3. And you do this 2 more times, correct? So these are your Px, Py, Pz, and these are your variables. Hold on. This should stay. Yes. Nobody said why you did that. Because if you remember, the columns are the same term variable. So we do this 3 times because we have 3 values. Same thing with respect to D2, 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 same thing, theta 3, theta 3. Yes.
When we wrote J omega, why did you use?
I may miss it.
Yeah, I was going to say.
Here, that's Z3, is not the in the picture. Negative S1, C1. Do you know what was this question? Because I needed to grab Z3, but here instead I put Z. This is not Z. Because why? The end effector doesn't have a joint, right? Joint 3 has a joint. So it was a mistake there.
Second column for J omega algebra.
This one because it's prismatic. There's no contribution in revolution in angular velocity. So it's very easy when you look at a robot, like, oh, okay, I can write the j omega part of it. JV is usually the hardest one because your revolute can have a contribution in your linear velocity. Good. All right, that's all. Like, this is everything we needed to know about Jacobian and how do we use it in calculating velocity kinematics. Now, it's up to you to choose which one for your application. All right, so what else do I have here? Since I took the class participation, you don't do this, so it's not available. It will show up next week though. Don't worry about it. It will show up. But I didn't want to leave you like with a bad memory for fall break. I wanted to send you off. So for the singularity, I think I never talked about it, especially about the example. I'm still creating it because I'm reading through everyone's submission. But so we saw in the 2-hour example we had, this example, our Jacobian is 6 by 2, right? So you can't find the determinant of that. But we can get the determinant of an expression. So if you get the determinant of this part, 0, 0, 0, 1, 0, 1, well, it's going to be 0, 0, right? It's not going to give you any information. So we can use the reduced Jacobian and then find the determinant of that. So this will be a reduced Jacobian, and then if you find you see that singularity has k times 5, k0 is 0, k1 is 5, as you saw, the arm will rotate back to its origin, so it doesn't matter how you move, then the vector doesn't move. And this one would reduce one with your freedom, right? So be careful whenever you are talking about singularity, you have to actually look at the robot. Don't just rely on math. Verify always with the actual robot. I think for CP solution, I also addressed the lecture that I actually solved the whole thing. And there is like configuration, so you can look at it. I think it was the previous lecture, the lecture before that. So that's all I had for today because I want you to focus on program assignment. Who hasn't heard from their teammates? Don't raise your hand now. Oh, I said you. Come here because I'm leaving time to discuss those cases and if you have questions. I can stay here until 4. So if you don't have a question, good luck. See you on Wednesday. If you have questions, you can ask.